Recall that a diagonal matrix is a matrix like this one, in which all the non-zero entries lie on the diagonal. In other words, all the entries that are off the diagonal are zero. Diagonal matrices are much easier to work with than just arbitrary matrices. And for that reason, it can be helpful to diagonalize a matrix or relate it to a diagonal matrix when possible. In this video, I'll explain what diagonalizing a matrix means and how to do it in some situations. As we just reviewed, a diagonal matrix is a square matrix whose non-zero entries all lie on the diagonal. A square matrix A is said to be diagonalizable if A can be written in the form P times D times P inverse for some diagonal matrix D and some invertible matrix P. So if A is an n by n matrix, then D and P need to also be n by n matrices to make the dimensions work out. Let's see what this means in an example. We're asked to show that this 2 by 2 matrix is diagonalizable, and we're given a very big hint to use this diagonal matrix and this matrix P, which hopefully is invertible. Recall there's a nice shortcut trick to finding the inverse of a 2 by 2 matrix. We swap the entries in the diagonal and negate the entries that are off the diagonal, and then multiply the whole thing by 1 over the determinant of the matrix. That's 1 times 3 minus 2 times 2, or negative 1. I'll rewrite this by multiplying through by negative 1, and we've got our P inverse. So now we need to check that A is equal to P D P inverse. In other words, we're going to multiply P by D by P inverse and see if that works out to A. I encourage you to pause the video for a moment and work it out for yourself before going on. Now, there's something interesting that happens when you multiply any matrix, in this case P, by a diagonal matrix, in this case D, with a diagonal matrix on the right. You end up just multiplying the columns of the first matrix by the corresponding diagonal entries. In other words, this is just the same as taking the column 1, 2 and multiplying them by 2 to get 2, 4, and then taking this column 2, 3 and multiplying it by 1 to get 2, 3 again. That's the output of that multiplication. Let's just see how that works. We're multiplying to get this entry 2, we're multiplying this row by this column, but since there's a 0 here, we're just really multiplying this first entry by 2. And to get this entry here, we're multiplying this row by this column, which again just multiplies the entry by 2. So this column just got multiplied by 2 to get this column. To get this entry here, we're taking this row times this column. Well, that ends up multiplying this entry by 1 to get this entry, this row by this column, which multiplies this entry by 1. So this column gets multiplied by 1. I went through that in such detail because we're going to use this fact in a moment. In fact, I'll write it out as a little note. So the note is, when we multiply any matrix M by a diagonal matrix, I'll call it E, so M times E, this multiplies the columns of M by the diagonal entries of E. All right, so now that we've got that note tucked away there, let's continue with the problem. So we still need to multiply this matrix by the P inverse matrix. And if we work that out, we get, let's see, negative 2, 2, negative 6, 5, which is exactly the A matrix that we started with. So indeed, the matrix A is diagonalizable, and these are the matrices D and P that do the trick. But what if we want to diagonalize a matrix like this matrix A, and we're not given the matrices D and P to do it? We have to find them. In other words, we need to find D, which is diagonal, and P, which is invertible, such that A is equal to P, D, P inverse. I'm going to rewrite that equation by multiplying everything on the right by p. So I get A times P is P times D times P inverse times P. Well, P inverse times P is just the identity, and anything multiplied by the identity is just the same thing. So this equation becomes A times P equals P times D. I want to focus in on the columns of P, so I'll draw attention to them by writing P as its columns concatenated together. And I also want to draw attention to the diagonal entries of D, so I'll write the diagonal entries of D out like this. So let me bring that notation into my equation, AP equals PD. So that's A times the columns P1, P2 equals the columns P1, P2 times this diagonal matrix here that we don't know what B and D are yet. But we do know, because we talked about it on the previous slide, that when we multiply this matrix by this diagonal matrix, we just end up multiplying these two columns by the corresponding diagonal entry. So this is D1 times the column P1, and then we have the column D2 times the column P2. And hopefully you also remember from the video about interpreting matrix multiplication that when you multiply a matrix by another matrix, that's just the same thing as multiplying the matrix by each column of the second matrix and stringing them together. You can just try that out for a couple of matrices and verify it. So this means that we're looking for vectors P1 and P2 and numbers D1 and D2 so that A times P1 equals D1 times P1 and A times P2 equals D2 times P2 so that these two sides of the equation will really be equal. Does that remind you of anything? Because it reminds me a lot of eigenvalues and eigenvectors. This is exactly the statement that D1 is an eigenvalue of A with corresponding eigenvector P1, and ditto for D2 and P2. So we found the key idea for diagonalizing a matrix. We look for eigenvalues and eigenvectors. That's how we build our matrices D and P. So let's get to work. To find the eigenvalues of A, we need to write down the characteristic polynomial, which we do by taking the determinant of A minus lambda I. So that's the determinant of 3 minus lambda, 1, negative 2, 0 minus lambda, which is 3 minus lambda times negative lambda minus negative 2, which simplifies to lambda squared minus 3 lambda plus 2, and that factors to lambda minus 2 times lambda minus 1. When we set that equal to 0, we have the eigenvalues lambda equals 2 and lambda equals 1. Now to find an eigenvector corresponding to the eigenvalue lambda equals 2, we need to solve the equation A minus lambda I times x equals 0 for lambda equals 2. That is, I need to solve the matrix and vector equation. Let's see, when lambda is 2, that gives me 3 minus 2, 1, negative 2, 0 minus 2 times x1, x2 equals 0, 0. And I can do that by writing down the augmented matrix. Let's see, 3 minus 2 is 1, 1, negative 2, negative 2, augmented by 0, 0. And I need to row reduce this to reduced row echelon form. This matrix is pretty easy to row reduce if I just take the first row and multiply it by 2 and add it to the second row and replace the second row with that. I've already got it in reduced row echelon form. This tells me that x2 can be free and x1 plus x2 has to be 0, so x1 is minus x2. So an eigenvector that I can use is just like any x2 and then minus x2 here, or in other words, x2 times the vector minus 1, 1. So I could just use the eigenvector negative 1, 1 to keep things simple. Now I'll repeat this process for lambda equals 1. So now I need a minus 1 times I times x equals 0. So that is this matrix times the x1, x2 vector is equal to the 0 vector. And I can row reduce the augmented matrix to 1, negative 2, negative 1, augmented by 0, 0. This row reduces to this matrix. So I have x2 being a free variable, and 2x1 plus x2 equals 0 means x1 is negative 1/2 x2. So my eigenvectors are of the form x2 times negative 1/2, 1, and so I can just use the eigenvector negative 1/2, 1 as my eigenvector. So now I'm almost done finding P and D. My D matrix is the diagonal matrix made up of my two eigenvalues, 2 and 1, and my P matrix is made up of the corresponding eigenvectors, negative 1, 1, and negative 1/2, 1. Notice that the eigenvectors need to be in the same order as the eigenvalues they correspond to. I will leave it to you to check that when we multiply P by D by P inverse, we get indeed our original matrix A. Here's a little interesting tidbit I want to point out before we move on. The matrices that you use to diagonalize another matrix are not unique, because we could have instead put the eigenvalues in the other order, 1 and 2, and then switched around the corresponding eigenvectors, and that would have worked just as well. So the process we just used for this 2 by 2 matrix can be used for any n by n matrix with n distinct real eigenvalues. The process goes like this. First, you find the eigenvalues, lambda 1 through lambda n, and you put them in your diagonal matrix D. Then you find an eigenvector for each eigenvalue. Let's call these eigenvectors v1 through vn, and we make our matrix P by stringing together those eigenvectors. Now I should point out that it's not always necessary for the matrix A to have, the n by n matrix A to have n distinct real eigenvalues. Sometimes A can be diagonalizable even if it doesn't have as many distinct eigenvalues as its dimension. But this situation will cover all of the problems that will work in this class. So in this video, we defined what it means to diagonalize a matrix, and we showed how it can be done using eigenvalues and eigenvectors.